Hey guys, in this video I will explain drag force in liquid when objects are moving in a liquid and they are acted by a viscous force. First of all, let's learn what the viscosity is. Actually, viscosity is resistance to deformation. Look at this animation. From left to right, the liquids are pouring slowly and slowly and slowly. The last almost is not pouring. So a viscous fluid with a high viscosity, such as a concentrated sugar solution or an engine oil, will pour slowly. A low viscosity liquid, such as water, has a low resistance to deformation and pours quickly with little drag force. Okay, let's continue with the Stokes law. In 1851, the Irish scientist George Stokes derived theory for a drag force, but it's called more properly the viscous force, acting on a small sphere that is moving through a viscous fluid. Guys, be very careful about that. First of all, I will explain the small sphere, the spherical shape. According to aerodynamics of shapes, it's not very easy to find a general formula for all different types of objects or different shapes. It's very difficult. So, first of all, let's derive a formula for just a small sphere moving in a viscous fluid. And then, if we have time, we'll continue for the other shapes. Stokes' assumptions. Number one, the flow is laminar so that layers in fluid flow smoothly past each other without mixing. The alternative is turbulent flow where the layers mix and the whole of the fluid swirls about in a random manner. So forget about turbulence. It is just laminar flow. Number two, the moving particles are spheres with smooth surfaces, as I mentioned, just a spherical shape. Number three, the fluid is homogeneous. It is uniform in composition. Everywhere, all along the liquid, you should have the same density and same composition. Okay. And the last is particles do not interact. As you see, the falling objects in different tubes are totally independent of each other. They mustn't have any interaction. So based on these four assumptions, I can derive the drag force. Let's suppose that the object is moving downward, so the motion is downward, so the drag force is against it in opposite direction of motion as usual. The drag force is going to be 6 pi eta RV. What the eta is, it's dynamic viscosity. What the R is the radius of this sphere. So as you see, the larger the sphere, the more the drag force. And the last is the speed as usual. I always expect to have larger drag force when the object is moving faster. Very similar to the case when the object is in free fall in the air, as I mentioned. So let's continue with dynamic viscosity. Viscosity actually is a quantity. And so I'm gonna explain the SI unit of viscosity. SI unit of viscosity will be the same as the unit of pressure, is Pascal. For example, the dynamic viscosity of water is 8.9 10 to negative 4 Pascal in average in a range of temperature, whereas the dynamic viscosity of honey is up to 20 Pascal. It's very important. This 20 is not exactly for all types of honey and all different temperatures. So if you ask me, does temperature affect viscosity? I will say yes. Yes, it does. Viscosity is also temperature dependent. For water, eta varies from about 1.8 millipascal to 0.3 millipascal as the temperature raises from 0 to 100. As you see here, on the left side, I have honey in 50 degrees Fahrenheit, and the right side, the temperature is high, maybe 70 degrees Fahrenheit. As you see, the sphere is falling much faster, and the last really fast, 100 degrees. So we expect to have less viscosity when the temperature is raising up. And finally, a question. A glass sphere of radius 4 centimeter is released in a swimming pool. It reaches a terminal speed of 0.5 meter per second. Find the drag force acting on the sphere. Dynamic viscosity of the water is 8.9 10 to negative 4 Pascal in that temperature. Okay, let's start with the formula 6 pi eta RV. Eta is given in actually, as you see, in Pascal, so there is no problem with SI units. R is in centimeter. I must convert it to meter. Here you see is 4 centimeters, so it must be 4 times 10 to negative 2 or 0.04. And the last is the speed, which is 0.5 meter per second. So fortunately, it's in SI units. And finally, the drag force will be 3.3 10 to negative 4 Newton. You may ask, okay, can I use this drag force to find the terminal speed of an object when it's moving through a liquid? Uh, it is not enough, no. Still, we have something to learn, the buoyancy force. And finally, you will be able to find the terminal speed. So be patient. In coming videos, I will explain the buoyancy force, and then we will be able to find the terminal speed. I appreciate your participation. I appreciate your attention. Thank you very much for watching this video. See you very soon.